functions out of non-functions, and I kind of never thought about it that way. Like, is there a name for that process of making
functions out of non-functions? I'm not sure what you mean by
so like the trig functions are made out of the unit circle. Like they're made out of something that isn't a function.
So take a point on this circle, right? What we're doing is we're creating a function that's dealing with the angle and just, let's say, the x or the y coordinate, right? If you're dealing with cosine, then you're saying you're somehow creating a relationship between the x coordinate and the angle. And that relationship is a true function, because if you give me the angle, I can only give you one answer, right? One input, one output. So even though it comes from a picture that is not a function, you can still, there's no name for the process. In fact, later on in this class, we will learn you can draw a circle and it is a function, like as a function.
Yeah, I guess what my question, like what I realized that my first question really was like why, I guess it was kind of like why aren't these not functions if they come from something that isn't one? But it's like talking about one aspect of that relationship.
That's right. It's the picture, you're looking at a relationship within that picture, so and you're creating a function from there.
That is a function. Well, the circle itself may not be a function, the relationship is.
Yes, and there might be many other relationships. Those are just two of them. Sine and cosine are just two of the relationships, but there could be, you can find others, right?
Yeah.
Okay, so we have the precise definition for these, right? Hyperbolic sine and cosine. Now, hyperbolic tangent is just what you would think it would be. It's just the ratio of sine hyperbolic and cosine hyperbolic, just like it was in the others. And then the rest of them are also the same. Hyperbolic cosecant is the reciprocal of hyperbolic sine. Hyperbolic secant is the reciprocal, right? This. And then cotangent. So once you have the hyperbolic cosine and hyperbolic sine established, all the others kind of just fall out from it. Yes?
Are those asymptotes that you talked about earlier defined by hyperbolic cosecant and hyperbolic cotangent? Since those are the only ones that reach undefined.
Yeah, we will have asymptotic behavior in some of these. Let's take a look at the graphs of all of them, all right? So I talk about the catenary here, all right? So we already talked about the catenary. And then here are the actual hyperbolic trig functions. So as you can see here, this is the sine hyperbolic trig function right here. That's the graph of it. And then here's your cosine hyperbolic, your catenary, right? There's your catenary. And then tangent hyperbolic is the ratio of those two, right? You can take the sine hyperbolic divided by the cosine hyperbolic. Wait a minute, hold on a second. Think about this for a second. If I'm going to take the red graph and divide it by the green graph, right? If I'm going to do that, does the green graph, is the cosine hyperbolic ever equal to 0? Does the green function ever hit the x-axis? No, which means the tangent hyperbolic will have no asymptotes, because the bottom, right? Tangent hyperbolic x is sine hyperbolic x over cosine hyperbolic x. And the cosine hyperbolic x is the green one, is never 0, so you should never have division by 0. So when I graph this, no vertical asymptotes. There it is. Weird looking, but that's it. You don't need to memorize these. It's not important. The catenary is probably the biggest one.
What's a vertical asymptote one more time?
When the denominator is 0 and the numerator is not. So you have, we're going to have, how about cosecant? Let me take these out of here. What about cosecant hyperbolic? That means sine hyperbolic's in the bottom, right?
Yes.
Is sine hyperbolic, that's the red one, does it ever have an x-intercept?
Yes.
Right here.
Yes.
So the sine hyperbolic is 0. We should have a vertical asymptote at 0. There it is.
Oh.
Right?
Oh, so when you were saying earlier that the cosine hyperbolic is not 0, you were talking about equation, the output of that.
The output, the graph never hit the x-axis, which means the graph is never 0. Like the graph has no zeros or no x-intercepts. Yes, sir?
If you have a denominator in general,
Mhm.
you have a vertical asymptote?
No, you don't have to. Only if the denominator is 0 at the same time the numerator is not. They can also be 0 at the same time, in which case you have a hole in the graph. And then here's your hyperbolic secant. You see this one doesn't have a vertical asymptote because the denominator of that one is the cosine hyperbolic, which again doesn't have an x-intercept. So that looks almost like a standard normal bell curve distribution. It's not, because that's a whole other function.
Yeah, it's too low for that.
Yeah, but it's we'll study that more later. Cotangent hyperbolic will. Okay, so that's what they look like. They're weird, right? The whole point of this is that when you look at all these together, right? Remember our sine and cosine? Sine and cosine looked the same, didn't they? Pre-cal. Sine and cosine looked the same. They were just phase shifts. Here, hyperbolic sine, hyperbolic cosine do not look the same. Okay? Do you remember in pre-cal that secant and cosecant had all those little those looked similar, didn't they? Not here. Okay, these don't look the same. All right, we're moving on. All right, you remember the Pythagorean identity? Of course you remember the Pythagorean identity. Sine squared x plus cosine squared x equals 1, pre-cal. Right, everyone got that tattooed on their arm, right? We know that from pre-cal. One of the most important identities in math, right, is the Pythagorean identity right there. Sine squared theta plus cosine squared theta equals 1, or sine squared x plus cosine squared x equals 1. Look at the identity for hyperbolics. It's almost the same, isn't it? And does it make sense? Remember the equation this came from, the hyperbola? It was x squared minus y squared, right? The x coordinate squared minus the y coordinate squared equals 1. So yeah, but we're going to prove it. We're going to show that this is true. I want to show that when you take the cosine hyperbolic function, square it, subtract the sine hyperbolic squared, that you should get the number 1. Right? So this goes back again to like pre-cal. How do we prove identities in pre-cal? You start with one side and you turn it into the other. You're not allowed to treat this like an equation and work with both sides. You have to start with one, transform it into the other side. So I'm going to start with the left-hand side. I'm going to write both of those down like this, and then I'm going to see if I can turn it into 1. So first I'm going to write down cosine hyperbolic, which is this. Does everyone agree that's cosine hyperbolic?
Yeah.
Yes?
Yeah, 'cause it's plus.
It's plus, but I need to square it, right? So I'm going to take that thing. I'm going to use a bracket, even though I personally would prefer to use parentheses again. I'm going to use a bracket just so you understand that that's the hyperbolic cosine function being squared. I'm going to subtract from that. Now I'm going to square the sine hyperbolic, which is 1/2 e to the x minus e to the negative x. All right? And I'm going to start manipulating this and see if I can't convince you, me, that this is just the number 1. So starting with the first piece here, I'm going to square something that's being multiplied, right? You see that multiplication between these two? Same with these? If you square a product, you can square each one. Like if you have x times y and you square it, that's x squared times y squared. That's basically what I'm doing here. So I'm going to take the 1/2 and square it. 1/2 squared is 1/4. And then I have to square this whole thing, don't I?
Yeah.
Okay, I'll do that on the next step. E to the x plus e to the negative x. I've got to square that. Minus, I'm going to square this one, 1/4. And then I've got e to the x minus e to the negative x. I've got to square that. Questions on that step? How do you square a binomial?
Can't you add? Oh,
How do you square a binomial?
multiply the exponents.
How do you take a binomial and square? You have to FOIL it, right? You have to FOIL it out. You have to do x plus y times x plus y.
When you do e to the x times e to the negative x, don't you get 1, no, you get 0.
Let's see what you get. I'm going to do it on the side here. Let's do this one right here. I'm doing different colors so you know what I'm doing. I'm about to do this over here. I'm going to do e to the x, it was the plus e to the negative x times itself, right? So times itself, e to the x plus e to the negative x. All right, FOIL away. E to the x times itself. E to the x squared, right? Which is the same as, I'm going to write that down here. E to the x times e to the x is e to the x squared, or you could write that as e to the 2x, because you could either say, hey, look, same base, multiplication, add the exponents, get 2x, or you could say it's this times this, so it's this squared, and then use a property of exponents that says something to a power, you multiply the powers and get 2x. No matter how you look at it, you should get 2x here, right? As a power. So that's the first multiplication. So e to the 2x. All right, now, next one, here to here. I'll do that right here. You're doing e to the x times e to the negative x. Right, that's what you're doing? Let's do the one where you add the powers, because, right, x plus x gave us 2x. Let's add these. What's x plus negative x? 0, right? So that's e to the 0, but what's e to the 0? 1, because anything to the 0 is 1 except for 0 to the 0. So I should get a plus 1 here. And then the middle one, wouldn't that be exactly the same thing? Plus 1 again. And then when I do here to here, I get plus e to the, I'm doing negative x twice, right? E to the negative x times e to the negative x is e to the what? Negative 2x. Because you're adding negative x plus negative x, so e to the negative 2x. And then I could put the 1 and 1 together and get 2, yeah? All right, so let me go back over here. My cursor's in the way. So I have here a 1/4 in front still, right? 1/4, parenthesis. Then I had e to the 2x plus 2. I added the 1 and 1 together. And then I had plus e to the negative 2x. Oh, there. Done with that part. Continuing, minus, right? Minus 1/4. Okay, then I have to do this multiply together, don't I? So I'd have to go through this process again? What's the difference, though? What's the only difference? We have minuses between here, don't we? So if this was a minus and this was a minus, would this change? No. Would this change? To what? -1. This one? -1. Last one? Same, right? Because 2 negatives multiply to be positive. So we should basically get the exact same thing except a -2 instead of a +2, right? Do I need to go through it?
When you're, I guess, factoring it,
Foiling it? Expanding it? Multiplying it out? Yeah? It's all right.
when you're kind of writing it out, it's e to the x minus e to the negative x, and then it's the same thing on it's the same exact thing on the other one?
Yep, exactly. Yeah, because look, here we're taking it and we're squaring it, right? So it's that times exactly itself.
Okay. It's only for perfect squares where one's positive, two x.
Difference of squares. I think that's what you're thinking. Yeah.
Last question.
Yes.
Just, why is it called FOIL?
I didn't make that up. That's for binomials. When you have binomial FOIL, you've never learned FOIL? I don't like FOIL. It's called expansion, and technically it's expanding the expression, but FOIL is cute and people like it. Is there a question? No? All right. Do you want me to work through any of it? You sure? All right. So what goes here is this line right here, e to the 2x, but -2 instead of +2, and then plus e to the negative 2x. We're almost there. We're almost there. So now, erasing some of this, let's distribute the 1/4 through both of these parentheses. And I'm going to scroll a little bit so that I can have a little bit more space down there. So when I distribute 1/4 through, I get 1/4 e to the 2x. A fourth of 2 is a half. And then 1/4 e to the negative 2x. And I'm done there. And then I keep going over here. Minus 1/4 e to the 2x. That's because a negative times a positive is negative. And then negative times negative gives me a positive half. And then a negative times a positive gives me a minus 1/4 e to the negative 2x. And who sees what happens now? Everything cancels except the halves. Right? This right here cancels with this one. And this one cancels with this one. And so all you're left with is a half plus a half, which is 1. So we have verified the identity. Yes?
There's something I learned in my previous class.
Yeah.
It's like you take the GCF of the whole thing.
Wait, you learned
You
what?
take the 1/4 of both of them.
Mm-hmm.
You put it outside and you put the bracket and you do the like.
Oh yeah, we could have done that. Here, since they both have a 1/4, we could just pull the 1/4 way out, and then you wouldn't have, and then you would have wound up with a 4 inside,
Yeah.
and then the 1/4 of 4 would be 1. Yeah, so it's just a different algebra path that gets you same place. Yeah, I thought about doing that, but I decided to distribute it instead. Yeah. Okay. Understand? So that is verification of an identity. That's a really, really like fundamental identity for hyperbolic trig functions, right? Just like the Pythagorean identity is a fundamental idea in pre-cal. I'm erasing, yeah?
I have one question.
Yep.
If those final two parts where you're starting canceling each other out,
Yep.
do you consider both of those to be in parentheses?
Both of those to be,
So from the up to the subtraction, up to the minus, would the final two, would those be correct?
these?
No, below you.
No, we removed the parentheses when we distributed the negative 1/4 through. The parentheses went away.
So so you would consider the whole thing to be like, to have
But
two
it's just-
or equal to it?
It's just one big expression, a bunch of terms separated by addition and subtraction. There's no more parentheses involved. Yeah, I'm not sure what you're asking, but it's kind of like if you have this, right? And you distribute the negative 2 through, there's no more parentheses. I don't know if that's what you're asking, but I mean, there's no more parentheses because you've distributed.
It's not what I'm asking, but it's hard for me to describe it.
Okay, think about it. Get with me afterward if need be. All right, so that's one identity. Did we have a few identities in pre-cal? Were there a few of them?
Yeah.
There's a whole page of them, right? So you have to imagine that there's a whole slew of identities when it comes to hyperbolic trig functions. And here's a bunch of them, all right? These are all on your formula sheets, all right? We could go through the process of trying to prove these. And in fact, if you've got some free time watching the games this weekend, you just want to break out your Cal stuff and try and see if these identities are true. We proved this one, right, just now? But you could go and try and show these are true as well, all right? Some formulas, all these things, right? All right, so everything we've done up to this point is just to kind of hey everyone, there's these things called hyperbolic trig functions. Okay? That's not what we care about. This is a calculus class. If they're functions, we saw their graphs, right? We saw the graphs of these things? Then they should have derivatives, right? We should have slopes of tangent lines. So we're interested in now, what are the derivatives of those 6 new hyperbolic trig functions? Right? And that's ultimately what we want to answer now. Well, I have good news and bad news, however you want to look at this. In Cal 1, the derivative of sine was cosine, right? Well, guess what? Hyperbolic, the derivative of sine hyperbolic is cosine hyperbolic. Yay, right? I'm going to prove that one to you quickly. I'm going to prove it to you that that's true. All right, so here's how I'm going to do it. I'm going to take sine hyperbolic x. I'm going to take its derivative. But the definition of sine hyperbolic, I keep on wanting to erase that scratch, is 1/2 e to the x minus e to the negative x, right? That is the definition of hyperbolic sine, right? I'm going to take derivative of this right now. So 1/2 comes for the ride. And then I take derivative of each of these two terms independently of one another, right? What's derivative of e to the x? Itself, okay? Okay, minus. Now, what's derivative of e to the negative x? Be careful. Itself times -1, right? Chain rule. The derivative of this is itself times the derivative of what's up here, which this time is -1. Right here, there's chain rule, but the derivative of x is 1, so that's why we don't need anything there, right? But here we need an additional -1 there, don't we? So it becomes minus becomes plus. And what is that? Cosine hyperbolic x. Right? That's the definition of cosine hyperbolic x. Right? Yeah, that's nice, right? So you can also show that when you take the derivative of cosine hyperbolic x, you get sine hyperbolic, but not negative. Remember in Cal 1, derivative of cosine was negative sine. Here, they're both positive.
That's so nice.
Yeah, wish it would have been like that in Cal 1, right?
I'm never going back.
Yeah. All right, so that's it, and then we keep going. Yeah.
So for the hyperbolic functions, we can just like express hyperbolic sine of x just as an equation. What would it just be?
As you can express it as this
Yeah.
expression.
Yeah. So
Yeah.
what would it be for just normal sine and cosine? Like what would does sine and cosine have a simple little? Right?
Not a simple one. The question is actually a good question. This right here, what we're saying is this hyperbolic sine function can be expressed pretty easily as just a combination of some exponential functions. The question was, is there an easy way to express sine, like back pre-cal, can we express sine in a similar manner? And the answer is that we can't do it easily. We can define it as like, opposite over hypotenuse, or we can define it off of a circle as being the y-coordinate divided by the radius. But you're saying, is there an easy way where it just has like x in there, just like this, right? So there's not an easy way, but there is a way, and we will do it later this semester. So I'm going to show it to you. It's this. Sine x equals, how ugly do we want to go here? Sum n equals 0 to infinity of, 1 over 2n plus 1 factorial x to the 2n plus 1. That's what sine x is.
Why is math yelling now?
And then but that looks terrible. All it really is, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus so on and so forth. This is what's known as the Taylor series, or Maclaurin series for sine. It's an infinite polynomial. It's a polynomial that goes forever, all right? And we're going to learn this chapter 8. Okay, we're getting the carriage in front of the horse here. But you asked, so there is a way to express sine in a manner in which it's just got x's in it. It's actually not that bad, except for the fact it goes forever. Okay, we'll deal with that later. It turns out that this is what your calculator uses when you type in sine of 2 or sine of 4 or sine of anything on your calculator. This is exactly what your calculator is doing. It has no idea about opposite over hypotenuse and all that. It has no clue. It does this right here. So we'll get to it. All right, so we have the derivative of sine hyperbolic is cosine hyperbolic. The derivative of cosine hyperbolic is sine hyperbolic. The derivative of tangent hyperbolic is secant hyperbolic. These are all in your formula sheets, okay? Go to your derivatives page, and you'll see all the derivatives of the hyperbolics on there. Do y'all see them? Yeah, they're all there. No need to memorize all of them. I think the first three are good to know, you know, especially in a physics class if you're going to be working with catenaries. It's good to know that the derivative of cosine hyperbolic is sine hyperbolic. All right, moving on. Because we now have a new set of functions with derivatives, then we should be able to find derivatives using product rule, quotient rule, chain rule. Everything we've had before, we can now incorporate into these new functions. So here's a function, y equals x times hyperbolic secant of e to the x, and I'm asking you to find the derivative. Okay, product rule, right? So we say y prime would be, here's our product right there, right? Our product. So the derivative of the first function is what? 1, I'll put 1, even though I don't need to, times the second function, plus, all right, what's the derivative of the second function? So it's chain rule, right? We're going to because it's hyperbolic secant of e to the x, but wait, what's the derivative of hyperbolic secant? I don't remember.
Negative secant times tangent.
Yeah, I'm coming to the formula sheets. Here it is. Derivative of hyperbolic secant of x is negative hyperbolic secant x tangent hyperbolic x. That, I need that formula, right? But instead of x, what do we have? We don't have x. What do we have? We have e to the x, right? So it's going to be, I'm going to put in parentheses, negative secant hyperbolic of e to the x tangent hyperbolic e to the x. That makes sense to everyone there? What I'm doing here is I'm taking the derivative of this right here. I'm in the middle of a product rule, taking derivative of this. I started with the outer function, which is the derivative of hyperbolic secant, which is that. But I still need what?
X. E to the x.
I do need the x, that's product rule, but I need the derivative of this still, which is itself, but I need it at the end of this, right? So I need next to this to finish the chain rule off e to the x, and then times x to finish off the product rule. So all of this right here, this right there, all the way to there, that is the derivative of that thing right there, without the x, sorry. Right? And then finish the product. So, but now we have all these new functions, right? All these, you know, you could do anything. I mean, I imagine a problem like this. Like, think about what would, if I gave you y is equal to, I don't know, sine hyperbolic of inverse sine of x squared. That's a chain, isn't it? So you start with the outer one, which derivative of sine hyperbolic would be cosine hyperbolic of this, times, now you need to take derivative of this, but now we're in last class, right? So you're doing an inverse, derivative of inverse, okay, I'm not going to do it. I'm imagining a problem. That's the way I make tests. I just imagine a problem. There's a problem. Yes?
So in terms of if you were giving us a problem like the original one,
Yeah.
how simplified would you want it? Like, would that be acceptable?
Unless we're actually doing something with that, like setting it equal to 0, solving, you know, unless we're doing that, I'm okay with just that.
Okay.
Yeah.
How did we get the final x at the end of the?
Product rule. We did derivative of this times this plus derivative of this times that. So that's our product rule just being finished off.
Okay, I forgot what it was. But I tried to remember this one, so I.
You're good? Okay.
Example of a practical application for hyperbolic.
What's that? I hear the voice. I didn't know where it was coming from.
Like a brief example of a practical application for hyperbolic trig function. Like in the real world, what would you use?
Well, I have one here with the wire where what we want to do is, and there's one in the homework as well, where what you're doing is you're trying to find if you have a wire hanging. Huh? Do they care about what? Oh, absolutely, because you know the wires have to be held. You know they have to be held with something that's insulated, right?
So if it like moves up, will it mess anything up?
Well, if you think, y'all know, like with the wires, you can't just attach it to the pole. The electricity would go straight down, right? So they have to use insulators, which are usually some sort of ceramic or glass or something like that. Those insulators are brittle. They have, certain tensile strengths. So when you have a wire hanging, they're attached to that insulator. You need to know vector stuff. You need to know the direction of the force, right? The direction of the force from that wire, right? So if you need to know direction of the force, you need to know the tangent to that curve, don't you?
So it'd be like normal vector things, but just plugging in the hyperbolic.
Exactly. So you have the function, right? You have the catenary, which is a hyperbolic cosine function, and you want to know at some point on that catenary, you want to know what's the slope of the tangent line. And so you take the derivative, and then you evaluate at that point, and you'll have the equation of the line, then you have the slope, and then, yeah. So, I mean, there's a homework problem just like that, where it asks you for exactly that. So I don't know, is that okay? This is a practical?
Yeah.
Okay. Yeah. I thought I saw a hand. Okay. All right, let's go back up. But I'll be honest, other than the hyperbolic cosine, the others don't come up that much. They don't. All right. Recap. Pre-cal, Cal 1, 6 trig functions, sine, cosine, tangent, blah, blah, blah. They're derivatives. So we had 6 functions, 6 derivatives. Last class, inverse trig functions, arc sine, arc cosine, they're derivatives, right? So we had 6 more derivatives, so we had 12. Now I just added the hyperbolics, right? 6 hyperbolics and their derivatives, right? Inverse is next. Each of these hyperbolic trig functions has an inverse function, and those functions have derivatives as well. Right? So rather than go through and actually derive any of it, I'm just going to give you what they are, okay? Let me see. Where are they? Where are they in my notes? Where are they? Hold on. Where the hell are they?
Is that not it?
See, derivatives of hyperbolic.
3.4? Like right above.
It's this.
There's inverse, example 4 is inverse hyperbolic.
It's like right above it, isn't it?
Yeah, it's probably up.
Like just.
No, it's not this. It's not this. This is the definition of the inverse functions. This is what they're defined to be. It's supposed to be this note right here, because it says the rest can be found in the book. Oh, wait, hold on. No. Here it is. I show the derivative of the inverse hyperbolic is this, and then I say the rest of them are in the book. So look on your formula sheets. Do you see the inverse hyperbolic trig functions? Are they on there? Yeah. Are there derivatives there?
Yeah.
Do you really just switch underneath the curve or under the denominator? Not exactly.
Yeah.
Looking at more. The changes.
Yep.
Are there the derivatives of that one?
Yep. Yep. It's the very last section on that page, right? The very last section. Question? Yeah.
The identities for the hyperbolic functions, are those on there?
They are.